Thank you very much, organizers, for inviting me for this wonderful workshop. And this is actually this is based on our recent papers on TMI, the deep learning COVID-19 features on CXR using limited training data. This is a collaboration, joint work with my students, Eugene Oh and Sang-Jun Park. As you know, that as of May 11th, 2020, there is already 4 million confirmed cases and also nearly 300,000 deaths. And so COVID-19 has been a very, we are suffering from the global pandemic of the COVID-19. In fact, there is no vaccines and also no treatment available. So only way to combat the disease and also flattening curve is early diagnosis. In fact, the golden standard for the early diagnosis, golden standard for the COVID-19 is based on the RT-PCR, reverse transcription polymerase chain reaction, because this is sensitivity is very high. However, the downside of that one is actually usually that in terms of time, it takes quite a while to get the result. Of course, latest development is now there is a very fast RT-PCR machines are currently available, but still, that's not widely used. And in that aspect, CT has also very good for the early diagnosis, because actually it has been reported the sensitivity is more than 90%. And also compared to RT-PCR, you can actually easily acquire the image and quickly diagnose it, for example, with the help of AIs as well. However, there are a lot of downsides for that. Of course, it's a more expensive system. And more important thing here is that because actually the routine use of the CT for the diagnosis has actually introduced some potential for the infection of the radiological suite. In most of the hospital in countries, usually the CT is used for other purposes as well, not only for the diagnosis of COVID-19. So after taking the pictures, you need to actually disinfect the radiological suite. It takes a while. So this is not a good way in most of the situations. In that sense, X-ray CT is a very promising direction because it's actually very quick and also it's very cheap compared to other CTs. However, the one downside of X-ray system is the sensitivity is low. However, but one good news is that the recent report that even in some cases whose initial RT-PCR was negative, but the CXR abnormalities are also obtained in about 9% of patients, which means there is some kinds of hopes we can actually utilize X-ray, chest X-rays for the diagnosis purposes. In fact, because of that one, a lot of people is actually utilizing the deep learning approaches to improve the sensitivity of chest X-ray imaging. For example, there are a lot of papers that are currently available, and we actually show some of the 3 representative papers. For example, one of the paper, COVID-19, is especially popular in the press and other literatures, and also they have open source available. And they actually reported that 91% of sensitivity in classifying the normal versus non-COVID-19 pneumonia versus COVID-19 pneumonia. And other researchers are mainly focusing on the differentiating between normal and COVID cases. And they actually even reported higher sensitivity. However, the problem in most of the cases, because actually, for example, and especially in the first cases, that's actually the most reasonable situation you can think about in the clinical environment. Even in that cases, in non-COVID-19 pneumonia cases, there is also different kinds of pneumonias and mix them together. For example, the data set usually they actually use has actually both bacterial and viral pneumonia as a one class of non-COVID-19. And there are a lot of reports that actually viral pneumonia, the radiological features are similar to the COVID-19 pneumonia cases, even for the experienced radiologists. So that means having this kind of categorization may not be practical in clinical environment. So in fact, actually, according to the study in 1998 in Lancet, so there are several types of pneumonia, and the common cause of pneumonia is actually For example, bacterial pneumonia is the most common type. And depending on the geological regions, then tuberculosis or TB is also quite a lot of portions as well. And compared to that one, viral pneumonia is relatively less common. So that means rather than categorizing with the viral pneumonia and bacterial pneumonia together, our goal is actually think about this kinds of potential triage. For example, if there's patients that coming in using the chest X-ray, we are interested in excluding the normal patient and bacterial pneumonias and TBs. And after that, because the viral pneumonia case is similar to the COVID-19, and using this pool, we are interested in utilizing RT-PCR or chest CT to actually have the final diagnosis of COVID-19. By doing this kinds of potential patient triages, you can actually save medical resources. For example, in many of the countries, the RT-PCR is now limiting resources, and also chest X-ray is also time consuming and also difficult to use. In order to do that, in order to use this kind of chest X-ray for the diagnostic purposes, there are several technical issues currently existing. The most of the important issue is actually limited training data. Actually, I noticed that there are a lot of questions about the patient data availabilities. In fact, this is actually the especially problem in this kind of global pandemic situation, because doctors are so busy dealing with this emergent situation. Because of that, they have no time to create this COVID-19 data set. So currently, only available COVID public data domain COVID-19 X-ray data is actually the collection of Cohen and Dar, and they actually collect the data from website as well as online publications. So this is actually some bias you can easily expect. And furthermore, many of the public domain pneumonia data set, which you can collect in the internet and all these resources, and many of them has an unbalanced age distribution, especially, for example, some of the data set have a children's coming from the Children's Medical Center. So because of that, it actually has some biases in data distribution. So because of that, if you actually remove these kinds of data biases, then you end up with a very small number of data sets currently available. For example, in our experiment, we only have a 500 data set, which can be used for the training and validation and test purposes. That can be actually obtained from the sources you can actually see in this table 2, which is currently available in the public domain. And so our goal is actually utilizing this kinds of small number of training data set to actually train the neural network. Of course, if the situation is getting better and then the doctors have some time to create the data, then you have more and more data available. In that case, of course, neural network can be more and more accurate. But still, at this pandemic situation, we still want to deploy some neural network architecture to deal with this kind of situations as well. So in order to deal with this kind of problem, we actually start investigating which kinds of biomarkers need to be addressed by using the neural network architectures. For example, in the chest X-ray, for example, in the standard biomarkers people often use in the computer-aided diagnosis, there are several kinds of features people often use. For example, lung morphology, or mean lung intensity, or standard deviation of lung intensities, or cardiothoracic ratio, which is actually ratio between the lung versus heart ratio, is quite often used in this kind of chest X-ray computed diagnosis application. But we actually investigate those things in the lung region, and we found that only standard deviation of lung intensity is a statistically significant biomarkers compared to other groups like a normal, TB, and bacterial pneumonia cases. So, however, this is actually very suitable for the radiological finding in COVID-19 cases, because there is a report that usually the common radiological features in COVID-19 is coming from the multifocal patchy consolidations or ground glass opacities. That has been actually reviewed in the previous talks as well. And that means actually the intensity distribution in the lung area is not uniform. So because of that, there is some kinds of variations of intensity values, which means this kind of thing need to be taken care of. But however, you need to actually think about this kinds of behavior in this data distribution has data quite a significant overlap each other. And that means this is not a correct, this is not a discriminating biomarkers to actually differentiate it COVID-19 versus other pneumonia cases. So and also this kinds of variation may be coming from the texture information instead of these kinds of patch consolidations. So we also, to actually differentiate these kinds of compounding effect, we actually think about investigate two distributions. One is intra-patch distribution, which means it's a standard deviation of each patch intensity histogram that actually presents the local texture information. And also another is inter-patch distribution of the intensity. It's a mean intensity variation between each patches. Each patches is now taken from the lung area with this kind of random locations. And then based on that, this is actually calculated. And then you actually see the distribution of this kind of scatter distribution. You can clearly see that the intra-patch distribution is not that much differentiating from other factors. But however, inter-patch intensity distribution is quite significantly different from other scatter plot. This means that in fact, this kinds of biomarker is usually coming from the consolidation, patch-wise, patch-different distributions. So because of that, it's better, we concluded that it's better to design a neural network to deal with these kinds of different kinds of patch-by-patch intensity distributions. So how can you do that? So based on this kinds of observation of biomarkers, what it design is this kinds of patch-by-patch classifiers. For example, this idea is following. So after lung area is segmented, now we are now having within the lung area, we are now taking the random number of the patches, 100 of patches, extracting them together, extracting the random location within this lung area. At the center of the patch is located in the lung area. And within this kind of mass, we actually using that one, putting the classifiers, and then based on that one, based on this one, you can do the majority voting. And from the majority voting, if actually the majority is classified as a COVID-19, we actually declare this is a COVID-19 class. If we actually do these kinds of patch-by-patch processing, those kinds of interpretability, like based on the Saliency Map, need to be modified as well, because in the usually Saliency Map people use, like a Grad-GAM based Saliency Map, is usually for the whole image cases. So we need to actually modify those kind of things. For that, in this paper, we propose so-called Probabilistic Grad-GAM algorithm, and we'll talk about that algorithm later a little bit more in detail. Okay. So, and I talk about a little bit more in detail each step by step. The first step we need to actually think about is actually the data normalization. Because actually, as I mentioned, the source of data is from all different kinds of sources, from different public domain sources. Because of that, there is a very diverse heterogeneities of the data. So for example, this is actually the normal, this is actually the scatter distribution between the lung area and heart area from the normal patient data case. If you actually distribute that one in the scatter plot, there is a clear separation between this distribution and this lung distribution. However, if you actually do this kind of data set, which is collected from by Cohen et al. From the internet and also papers, in that case, there are there are significant overlap between the heart and lung lesion in intensity values. That means the intensity is not actually biases depending on the sources. And this, if actually just directly design the neural network, even for the segmentation algorithm, with respect to this distribution, the result was not that good. So we need to actually do some kinds of data normalization such that at least for the area between the lung and a heart area should be separated like this. So for example, this is an intensity histogram for the normal data, and this is an intensity histogram from the Cohen et al. Data set, which is collected from the internet. And from here, you can actually clearly see the differences in their distribution. What I did is actually to correct this one, we actually do the gamma correction and some histogram normalization. And after that, you can clearly see the histogram is following the similar normal distribution, as well as you can clearly see the intensive value is separated between the heart and lung regions. And using this kind of data normalization first, and then you start to apply your segmentation algorithm and also classifier algorithms as well. For example, this is a segmentation result. Now you can actually see that some interesting behavior. For example, our only data set with the mask available is for the normal data set, which is currently available. So that means if you train your neural network for the segmentation algorithm for the normal data set, it really works very well for the normal data set, as you can see here. However, if you actually apply that segmentation algorithm for other disease classes, especially in the bacterial pneumonia classes, there are a lot of consolidation here because of that. The segmentation mask is not accurate, as you can see here. However, one of the interesting things that's actually the thing we want to exploit as well is this kind of this kind of morphology of segmentation is also can be utilized as a differentiating factor between normal and patient. In fact, we actually just used the binary mask, segmentation mask, and designed a neural network to classify the normal versus disease classes. You can clearly see that accuracy is 87%, which is quite significantly accurate. So with this kinds of morphologies, we can clearly see the normal versus patient data. However, our goal is not just like a differentiating between normal and patient. We need to actually differentiate between multiple pneumonia classes. From that, we need to actually differentiate the viral and COVID cases as well. So that means you need to actually take advantage of these kinds of advantages from the segmentation mask, as well as you need to actually design a classifier that is very suitable for this kind of mask as well. So for that, as I described, that we actually designed a patch by classifier with the majority votings as well. For example, when these kinds of patches, we actually trained the ResNet 18. This is a relatively small neural network size. I'll talk about the reason for that as well. And then for each random region, we actually classify in the 4 different classes. And then based on the majority of the classes, we actually declare whether this is a COVID-19 or normal or TB or bacterial pneumonia cases. Now, this is actually the classification result. What we compare here is actually global approach. Global approach means usually standard approach. People usually use image as it is and then put in all the new images to the neural network to train the neural network at one time. But because of the data is limited, and because we are now classifying 4 different classes, the accuracy of a global approach is not that good. 70% and specificity is good, but still it's not good. But however, by using these kinds of proposed patch by patch approaches, you can clearly see that accuracy is significantly improved, and also all those kinds of recall rate and all things significantly improved. Furthermore, one of the nice advantages of this kind of, another nice advantage of using this kind of patch by patch training is it is actually more robust for the small data size as well. For example, here, this experiment, what it did is from the training data, we are now reducing the size of training data from 10%, 30%, or 50%, or 70%, or 100%. Now you can clearly see that the performance accuracy of the patch by patch and also global approaches decreases, but still the decrease of patch by patch approach is more graceful. Especially if you think about the relative performance by normalizing the starting point together, you can clearly see that global approaches are suddenly decreasing performance if we reduce the data size by half. But patch by patch approaches actually has a graceful performance degradation, as you can see in this picture. So why this kind of thing happen? As expected, because we don't have any, not that much enough data available. In this kind of situation, if we try using the standard global neural network approaches, this is a training curve for the accuracy as well as F1 numbers. Now you can clearly see that there is overfitting behavior in this training curve. But however, if we do the patch by patch approach, patch-based approach as proposed in our method, you cannot see those kinds of overfitting behavior, because now we have selecting the random patches. Each random patches works as a data, separate data, so it actually have an inherent data augmentation behavior. Because of that, you can actually reliably train your neural network without concerning about overfitting. Furthermore, we also compare our method with the current state of art SOTA method. For example, COVIDNet is actually one of the SOTA methods which is currently available in the public domain. But as I mentioned, it has a limitation because it actually merges the bacterial and viral pneumonia cases into one classes, and just like differentiated between normal and pneumonia and COVID-19 cases. But even in these cases, we also trained our neural network using these kinds of categories as well to see the side-by-side comparison. Now, even in these cases, now you can see that the sensitivity of COVID-19 is about 80%, but our proposed method is actually increasing significantly, as you can see here. Furthermore, COVIDNet has a number of weight, trainable rate is 100 million cases. But however, in our neural network, because we are using the light neural network to actually deal with this kind of small data set, still with the same number of data set, with only 10% of weight, we can actually have a much more significant improvement, as you can see here. Now, the goal, of course, actually the goal of this AI is actually making the decision, but however, we also need to provide the interpretabilities for the radiologist as well. So how can I, that standard method to providing this interpretability is usually based on the Saliency Map. One of the most widely used Saliency Map is the Grad-GAM method. Grad-GAM method is, can be utilized for various neural network architectures. This is a weighted combination of the feature map as specific layers. And this weighting factor can be actually calculated based on the gradient back propagations. However, so even though this is widely used in many of the cases, but however, it has been reported that if there is a multiple area which is actually suspicious, or which is actually it can be categorized in one region, sometimes Grad-GAM is only like a focus in one of the regions, as you can see in this picture. So the Grad-GAM map is very blurry usually, and it's not differentiating multiple localization as well. And furthermore, this Grad-GAM is actually for the training for the whole images. But as I mentioned, to actually to deal with these kinds of biomarkers, and also to save the to actually use to utilize a small number of data set, our method is a patch by patch approaches. So that means this Grad-GAM algorithm need to be modified. But in fact, actually, there is a very natural modification of this Grad-GAM algorithm based on the what we call the probabilistic Grad-GAM. The idea is very simple. Each patches you can calculate the Grad-GAM for each patches, Saliency Map for each patches. But however, each patches has a probability whether that belong to COVID-19 classes or not. So now you are doing the probability weighted summation of this Saliency Map across all the patches. Then, as you can see here, you can clearly see the high resolution Saliency Map. You can clearly see the several suspicious region in the lung area very clearly in this kinds of probabilistic Grad-GAM, which has a much higher resolution, which is also gives a more detailed information compared to the standard method. And this is actually the application of probabilistic Grad-GAM we propose for different kinds of class data. For example, this if we apply the normal data for the using the COVID-19 saliencies, you cannot see any kinds of things. There is some small suspicious reason, but because the probability is so low, this is not highlighted. And also bacterial cases, there is some of the consolidations here, but because the probability is low, you can actually see that this is not highlighted. However, in the COVID-19 cases, you can clearly see that remarkable saliency maps as well as a detailed information of the reason which is suspicious, and also which is actually gives the interpretabilities in our decision making based on majority votings as well. In summary, so our goal is actually utilizing this AI for the patient triage using chest X-rays. Instead of actually just like differentiating COVID-19 from all the classes, our goal is actually from the chest X-ray data, we are now excluding the bacterial pneumonias and TB data. And now even among the viral and COVID-19 cases, which is even difficult for the experienced radiologists to differentiate between them, using this data, we just utilize RT-PCR or chest CT for the final diagnosis. By doing that, you can actually significantly reduce medical resources, use of the medical resources. In order to do that, to deal with this kind of problem under the limited data, training data situation, in our, we actually propose this patch by patch classifier design, as well as this kind of saliency map, which has a more accurate, more like a localized saliency information compared to the standard Grad-GAM approaches. With that, I'd like to conclude my talk. I'd like to thank all the doctors and nurses who is fighting with the COVID-19, and also this research is funded from our funding agencies, as you can see here. Thank you very much.